Bom, boa tarde a todas e todos e todes. É com prazer que a gente começa o colóquio do IME nesse ano de 2023. O colóquio a gente começou em 2019, né? Existiu o colóquio do MAP há muitos anos, e aí tomaram uma decisão de ampliar para todos os departamentos do IME. A gente teve um semestre em 2019 e depois, 2020, 2021, com a pandemia, teve, acho que 1 ou 2 edições, por causa e remotamente, né? E o ano passado a gente retomou e esperamos que esse ano a gente consiga fazer ele ainda melhor do que tem sido. E aí é meu prazer, vou passar para o Ricardo para apresentar o nosso convidado de hoje.
Bom, boa tarde. É um enorme prazer para mim, na verdade, estar aqui para apresentar o Gaetano, né? Ele vem falar sobre algumas ferramentas para estudar sistemas lagrangianos. O Gaetano é um velho conhecido do Instituto, né? Eu não vou falar demais aqui porque ele tem para falar, mas além de ter sido meu supervisor de pós-doc, na verdade o Gaetano foi colega, amigo do Baroni, professor titular já falecido do Instituto há algum tempo, né? E tem influência enorme no grupo de estabilidade da gente, amigo de todo mundo, né? Então, para mim é um enorme orgulho estar recebendo o Gaetano aqui. Acho que a última vez que eu ouvi falar, inclusive, foi aqui no aniversário do Baroni de 75 anos. Tá? Então, Gaetano, foi.
Obrigado. Gostaria muito agradecer aos organizadores, o Ricardo, a Cristina, o Bagné, a Sônia. Eu mandei título e resumo em inglês. Depois alguém traduziu para português e eu agradeço a tradução. Mas o meu português, infelizmente, é muito cansativo. O português matemático, outro talvez é pior, é muito cansativo. Então, eu vou mudar daqui a muito pouco para o inglês. E se alguém quer colocar perguntas em português, eu procuro tentar explicações em português ao pedido do público. De outro jeito, vou falar inglês. Deixe-me antes lembrar do nosso amigo, colega, mestre, Angelo Barone. Daqui a um pouquinho, tem o aniversário do seu falecimento. Ele faleceu há 10 anos, no dia 5 de abril, então faltam poucos dias. Eu gosto de lembrar dele com muito carinho e quero dizer que muita gente aqui sente a sua falta. Now, let's go to the talk. So the talk is about a simple tool to study Lagrangian systems that I developed together with other staff, with Gianluca Gorni from the University of Udine, Italy. I developed perhaps almost 10 years ago. We did several things related, and everything was motivated by the fact that I had to give a course on variational mechanics, and one of the main topics was Netter's theorem on variational mechanics. The unique infidelity of Emulator to algebra. You know that she was a very strong and great algebraist, but she is very known in the community of physicists and also of mathematical physicists and many other people, because of this result, which is not the aim of this talk. I'm not going to speak about the Emulator's theorem. However, talking the simple tool, I will not complicate trying to include the Netter's presentations, but anyway, it will be underlined, so I will give several hints about Netter's. So before starting talking about the subject, let me say a few words about what happened in those times. So we are in 1915, and Emulator is a mathematician of Erlangen University in Germany. She is the daughter of a mathematician, and she's already so known in the German community that Hilbert and Klein appointed her to Göttingen. Göttingen was the best place. Well, Hilbert was there, and so Emulator moved to Göttingen, where Einstein was invited to give a few lectures, I think, if I well remember, or at least one lecture on general relativity. General relativity was, there were the equations of general relativity, the equations which were made by Einstein, of course, with some help of Levi-Civita. So Einstein was always very, very grateful to Levi-Civita. He was saying that the best things in Italy are spaghetti and Levi-Civita, because it was Levi-Civita, what is called Einstein's tensor, the left-hand side of the equations, the right-hand side being the stress energy tensor. So the left-hand side is called Einstein's tensor, actually was made by Levi-Civita. So it was Levi-Civita who made the geometric form of the object used by Einstein for the theory. Of course, general relativity is undoubtedly by Einstein, not by Levi-Civita, but anyway, there was the contribution. And what about Emulator? Emulator was a specialist in symmetries, and so specialist. She worked in many things in algebra that I don't know, not being an algebraist. Anyhow, Hilbert's aim was to insert general relativity into Lagrangian dynamics. So his goal was to deduce from an action, a Lagrangian action, to deduce the equations as the Euler-Lagrange equations of that action. Of course, we are not in the framework of ODEs, as will be later. We are in the framework of PDEs, but the goal was that. And so he was able to join that goal. And if you see Wikipedia, the action, the integrand of the action is called after Hilbert. Somebody calls Hilbert Einstein, because also Einstein arrived at the same result. Whittaker says 5 days before Hilbert. So Hilbert certainly was the first to think about the Lagrangian formulation. Why the Lagrangian formulation of the theory is so important? Well, this could be a silly question to a physicist, a theoretical physicist, since everything is of this kind. Every field theory comes from an action, and the Euler-Lagrange equations of the action, so physics is that one. And why Emulator? Emulator is important because Hilbert said, well, we need an expert trying to explain conservation of energy and such kind of things in the framework of Lagrangian general relativity, which was an objective which was joined in a few months. At the end of the year, it was done in 15. And Noether was working on Noether's theorem. And after that, she returned to algebra and worked only on algebra till the end of her life. But for that reason, she was extremely important in physics. And actually, Hilbert immediately, now I am, perhaps I'm talking too much about history, but I think that you like me to talk about, about history and general things. Well, this is a colloquium, it's not addressed to specialists. So let me also add, we are close to the Day of the Women, so let me also add a particular which perhaps some of you don't know. It is that in 1915, Hilbert immediately tried to contract Emulator, but he couldn't, because there was the opposition of some philosophers or some historians, somebody of the humanistics, who said, gentlemen, our soldiers are going sooner or later returning back to the university, and will they learn on the feet of a woman? And Hilbert answered, gentlemen, we are not a bathroom, we are not a bath house, we are a university. What's this point of sex about university? This is not separating for bath reasons. Why you put this question? Anyway, the question was so important that Noether taught for 4 years under the name of Hilbert. So for until 1919, she was not a professor of Göttingen, and she was teaching, but formally was Hilbert. So Hilbert covered formally o jeitinho alemão. Este é o jeitinho alemão. Tudo bem. So much for history. But I think it was, the only less particular, so I was saying that Emulator, in the general framework of Lagrangian dynamics, she put the problem of conservation laws as derived from invariance properties of the Lagrangian action function. So it was something so important that when she died, well, in 1915 she was 33. She died 53, unfortunately, quite young, in the United States. Being a Jew, she had to escape from Europe, and Einstein wrote her obituary in the New York Times, saying that she was one. Well, you may find very, very easily the obituary, and you can see the Einstein's words on Emulator, which are due to this unique infidelity to, to algebra, because this was what Einstein appreciated most, I think, about, I'm sure, about her. So let us go to our stuff, which is in the framework of ordinary differential equations. So we have a smooth scalar valued Lagrangian functions. T is normal time. Q and Q dot are variables in Rn. Everything could be made in an open set of Rn 2n plus 1, but it's not important to be so detailed now. And this is Lagrange, Euler-Lagrange equation. Well, they are n scalar equations, or one vector equation, if you like. They are due to Euler. Then there is also Lagrange, but well, the first was Euler. Theorem. Let Q of T be a solution to the Euler-Lagrange equations, and let Q lambda T, lambda being a real variable, be a smooth family, smooth in both dependencies, of course, of perturbed motions. So we will see many of them, many families, but to give a first idea, you can take translation on Q1 axis. So for instance, you can have Q1 plus lambda, and then Q2, Q3, and all the other variables unchanged. Okay, this is a family. For lambda equal to 0, you have a solution to Lagrange, Euler-Lagrange. Now, I see. Q naught, the only condition is that Q naught equals the solution. So the solution is part of the family. The other functions are not supposed to be solutions. Sometimes they are, sometimes they are not. It's your choice. Then, this is the thesis of the theorem, the very simple theorem. The thesis is that this is a constant. This function of T is constant along the solution Q of T. So you see, I will repeat this formula many times. So finally you will certainly remember it. However, if this is something inspired by Noether theorem, and what Noether was thinking is are invariances families that make this disappear, the integrand disappear. So in that case, this is a conserved function. But what we are saying is that we also consider this part. And when I told Noether spirit, I mean in the particular case of ODE, and also in the particular case of families which do not change the time. Somebody could say synchronous perturbations of the solution, not asynchronous. In Noether spirit, there are asynchronous and synchronous everything, and also for fields. So also, I think that in Arnold's book on mechanics, the very simple, under Noether's theorem, you have the very simple synchronous perturbation result, only that. Anyway, if you didn't understand what I said about Noether, don't worry. Return to this formula. Just look at this formula. So, this is a constant along a solution. However you take a family, you have a constant of motion. And this, we will say, the constant of motion associated to the family. Well, obviously, the constant of motion is generally trivial, can be zero, or unuseful, something complicated you don't know how to, what to deal with, but anyway, it is a constant. And the constant is non-local because its value at time t depends on not only on the state of time t, q of t and q dot of t, but also on the whole history, because you have the integral part. So it is a non-local constant. The proof is straightforward. You just take the derivative. You just take the derivative. Here you have, with Leibniz, d over derivative in time of this time this, scalar product this, plus this times the derivative of this stuff. Here you have minus the integrand computed at t, and to compute the derivative under lambda, you take the derivative, the partial in q, time, scalar product q dot, and not q dot, the derivative of q lambda with respect to lambda, at lambda equal to 0. And together with this piece, you remember here we had the d over the derivative in time, the first term cancels because of the Euler-Lagrange equations. If you want, I can write in the blackboard, but I think that you followed. Well, the last term here is the derivative of L with respect, the partial derivative with respect to q dot times the derivative in lambda of q dot. And this cancel with the second term obtained by this by Leibniz rule, only reversing the two derivatives which are in the continuity assumption, smoothness assumption of the partial derivatives is guaranteed. Everything understood that is really trivial to check the formula. Okay, so let us use it. Well, I already said that perturbed motions were originally inspired by the mechanism that Noether's theorem uses to deduce conservation laws. Whenever the Lagrangian function enjoys certain invariance properties, so that integral term vanishes. But on the contrary, we are going to use the integral term in several applications. Well, it's 2:30, so in a few applications. The first one is Poincar half plane. So Poincar half plane it's something known, more or less known, you know. Well, not everybody knows, but it's something very simple. Poincar half plane is a concrete model for Lobachevsky geometry, hyperbolic geometry. So initially, hyperbolic geometry was an axiomatic theory, and then Beltrami produced a concrete model, produced a big result. Into it, there is a concrete model for Lobachevsky hyperbolic geometry, and also Klein produced an equivalent problem. Then you can read the story in the American Mathematical Monthly by Abe Scheitzer, how hyperbolic geometry became respectable in the American Mathematical Monthly. Yesterday I corrected the proof of my joint paper on the American Mathematical Monthly, exactly that is going to appear in a few days, I hope, online at least, exactly on this specific application on Poincar half-plane, which is something very short, a note. So, what's Poincar half-plane? Poincar half-plane can be described in variational ways, like the upper half-plane, you see, Q1, Q2, in R2, Q2 greater than 0, strictly greater, so it's the upper half-plane, whose geodesics, whose straight lines, are the solutions of the Euler-Lagrange equations of this Lagrangian function. You see, it's quadratic in the velocity, and here you have 2q2 to the square. So it's, if you want, for people like mechanics, it's a kinetic energy, a pure kinetic energy. Anyway, the solutions, the geodesics, have the following immediate first integral energy. Energy is the Lagrangian itself. And why they have this? Well, I could say check, but I don't say check because energy is such, every Lagrangian function which does not depend on t, you see, has this function as a conserved energy, and you check immediately by taking the derivative. And I'm sorry, I'm sure that half of you already saw these calculations many times and taught to second-year students, but they told me to be careful and try to give more details than possible, so I followed the instructions. Well, for a colloquium, it's good to be detailed in this elementary stuff, very elementary. So the blue terms cancel because of the Euler-Lagrange, and the other cancel because they are the same, you know, with opposite sign. In the actual case, the energy is the Lagrangian, because the original Lagrangian is quadratic. So if you take this formula for the energy, you obtain the Lagrangian itself. In other words, kinetic energy, as I already said. Now, another immediate first integral is the first component of the momentum, which is q dot 1 and over q2 squared. And I call this first integral as p momentum. This is a consequence of the lack of q1 in the Lagrangian function. So q1 is a cyclic coordinate, as Sonia knows. And no, I'm using Levi-Civit and all the terminology because I like that terminology. So the first Lagrange equations is this. minus this equal to 0. But this derivative is 0 because of the lack of Q1 in the Lagrange. So this stuff is conserved. dl over Q dot 1 is conserved. This is also trivial. So we have two trivial first integrals. The conservation of the first component of the momentum can also be deduced from Q1 translations family, which leaves the Lagrangian invariant, because the Lagrangian in our formula, this is a conserved quantity. Since the Lagrangian does not depend on Q1, the Lagrangian is invariant under this family. And so this disappears, and you have only the first term, which is precisely the conservation of the first momentum. I show this, even if it is trivial for other reasons, because I want to give hints to Netter. So much for immediate first integral. We have another first integral in the Poincar half plane. You easily see that, you know, this is a quadratic term and this is a quadratic term. So if you take the dilations, i.e. you multiply by e to the lambda q of t, you have both in the numerator and in the denominator, composite in the family, you have e to 2 lambda, so it cuts and it is invariant. So the L being invariant by dilations, you have the corresponding. What happened? Oh, I'm sorry. Thank you very much. So, having the invariance, the corresponding, our formula, in terms of our formula, the integral part disappears, and you have another first integral, which is this one, or this. No, or this, exactly, this. This is B. Okay, this. So we have three first integrals. The first two are trivial. The third is not. I showed the third because I wanted to make another hint with Netter to see how it is nice Netter. Anyway, now let us do something silly. So let us use Q2 translations. We know that this doesn't make any. It seems silly because it is not the Lagrangian is not invariant under vertical translations. This is our contribution. I'm going to see that with the Q. With the other translations, you get some kind of non-standard separations of variables, and you integrate the problem with the two trivial first integrals without use of the third, and you integrate very, very easily. Let us see how. Let us see how. So, if you insert the vertical translations, you have you make some computations, and by the use of the energy, which is a constant, you have the constancy of this non-local function, where only Q2 and Q dot 2 appear, and so the derivative is 0, and the derivative is a separate linear equation, trivial linear equation, which is immediately integrated, and after that, you plug Q2 of t here in the other trivial first integral, and you get Q1. So you have a separation of variables in a non-standard way. And for b equal to 0, the geodesic is a vertical half line. You see Q1 dot is 0, so it's a vertical line. Otherwise, and you have also the solution of the linear equation gives you also explicit solutions also in any case. And for b different from 0, by eliminating t, you have an half circle with center on the x-axis. The x-axis, the Q1 axis, is not part of the Poincar half plane. You see, the half plane is the upper plane, and so the result is this. You see, this is a geodesic. R is a geodesic. The thicker line is a geodesic. P is a point out of the geodesic, and all the other I'm showing you are geodesics. So you have a straight line, a point, and by this point you can design infinite parallel straight lines in the sense that they don't cross the original one. This is a hyperbolic geometry derived very easily only with a linear equation. Now, before going to the next topics, let me only remind you that there are beautiful Escher paintings which use hyperbolic geometry. If you see them, you immediately... and he was very accurate in studying hyperbolic geometry. So it can be something artistically used. Okay, let us see. We also did the separation of variables, non-standard separation of variables, that I will not show you because it is much more complicated. However, you can see in the paper, if you want. Also for the conservative Maxwell block equations, which model laser dynamics. For that case, which now we are in dimension 6, before we were in dimension 2, now in dimension 6, and we got two separate dynamics. One is the fish, and the other one is the central force dynamics. The details you find in the paper. All details, in the San Paolo journal of mathematics, in your journal. You see, there are only bounded orbits, but the fish, here you have an homoclinic orbit, an equilibrium, another equilibrium, and these dotted lines belong to the fish dynamics, but do not belong to our stuff. So we have we separated into part of fish dynamics and central force dynamics. Okay, so you have not to think that you arrive at unbounded orbits starting from tori, because it's an integrable systems, and all orbits are on tori, so they are bounded. Okay, I only wanted to show this as to see that there is another application on separation. Now, let me tell you about energy conservation. energy conservation, we can revisit energy conservation from our point of view. Why I'm doing this? I'm doing this preparing ourselves to see why, how we find a family to start to study mechanical systems with the dissipative forces. And first, we consider energy conserved. And I want to show the details. So, how can we have conservation of energy from our formula? Our formula, in netter spirit, you should change time. But also with our formula, you can have energy conservation. Look at this trick. You consider time translation family, and this is the integral, the integrand of the integral part of our conserved quantity, and it is computed at lambda equal to 0. So it is the derivative of L. This different L is to see, you see, to show that there is no time, explicit time dependence. So the L over Q times Q dot, this is the scalar product, plus the L over Q dot times Q2 dots. You see, when you derive with respect to lambda, you are taking a dot, and lambda equal to 0, you have Q2 dots. So actually the integrand is of our formula is the total derivative of the Lagrangian function composed with the motion. And so what? So the constant of motion is del over Q dot times Q dot minus L plus L at Q naught, a trivial, up to this additive constant, you have energy. You see? Why I showed you this? Let me, for completeness, let me say that in the case of this Lagrangian function, kinetic energy of a particle in dimension n minus a potential, the energy is kinetic energy plus potential energy, as every kid of physics knows. Now, dissipative mechanical system with viscous resistance. Consider K greater than 0 a smooth potential function, and this is ma equal m acceleration equal force. There is a linear dissipation. This is a linear dissipation, and this is minus the gradient of the potential energy. So a potential force and a dissipative linear force. Very well. So in this case, for k equal to 0, you have energy, the first integral of energy. For k greater than 0, E dot, it's a very simple trick that also that shows that the energy is decreasing. Well, everybody knows even this. I'm telling a lot of things that everybody knows. Well, I like. So, in the sequel, U, the potential energy, is bounded from below. So, U greater or equal than 0, you put the lower bound 0. It's not important where you put the 0. And so Q dot is bounded in the future because the kinetic energy is less than the total energy because U is greater than 0, greater or equal than 0. And this is the energy is a decreasing function. So this is less than the value of energy at the initial moment. So you have a bounded Q of t for bounded intervals of time, and so you get a global existence in the future. Of course, in the case k equal to 0, you have global existence also on the past, because future and past, without dissipation, they can treat it similarly. But what about global existence in the past with dissipation? I put the question to many people. I don't tell you the names, but even people with very strong, I wrote emails to a lot of people. Do you know a general result about global existence or not in the past for dissipative systems? You see, our equation can be put in the Euler-Lagrange variational setting by this exponential at the very beginning. So this is the usual Lagrangian for the conservative case, and this is the exponential. The trick is I can do in 2 minutes, but you can imagine that taking derivatives, the exponential function cuts because it is in every term, and you get exactly this equation. If you don't believe, check in 2 minutes, it's trivial. Okay, so now we have our tool, a nostra ferramenta, and we have this function. So which family you use? Well, we didn't have much to think about because you see, we use this family quite immediately because for a equal to 0, this disappears, is equal to 1, and you have time translation. The time translation is exactly what you used for the conservation of energy in the conservative case. In the dissipative case, you have an exponential in front. So let us put an exponential with another parameter, and let us say whether it works for some values of the parameter. It is quite logical. And you arrive at something quite complicated. Doing the computations, we use the differential equations to cut the Q2 dots. But what is interesting is that there is a value of k that is the value of A is a new parameter. You can specify a value of A so that this term disappears, and you have a derivative, a total derivative, and a function here which is positive. So you have something like very interesting. So for A equal k to m, which is the obvious choice, you have this constant of motion, which becomes something with a positive integrand, so something which can be used as a Lyapunov function. Since u is greater or equal than 0, the blue integral decreases for t less or equal than t naught. When this goes up, the interval reduces, and this is positive. So the blue integral decreases, so the red function increases, and you immediately have an estimate, because this increases, so this is less than the value in naught, and you take the exponential to the other side, and then you observe that mq, the norm of q dot square, is less than this guy, because this guy is positive. So this less than this less than this. You saw, like for Lyapunov functions, in a bounded interval, the velocity is bounded. So also q, and we have a global existence of the solutions. Now, since I have only 7 minutes, no less, 5 minutes, I only tell you that for homogeneous potentials, we found so a Lagrangian with kinetic minus a homogeneous potential. We selected a value of the homogeneity, -2, where which is the case of Calogero potential, the scattering of Valdir worked on this stuff many years ago with the scattering of line. This is a Calogero or Calogero-Moser system of particles on the line, and so we can have a property for all these potential, not only Calogero, all homogeneous of -2 of degree -2, and you have I don't show you the details. You have the time dependence of the distance from the origin, this, even though you don't know the shape of the orbit So we generalize the formula known in the central case. The central case was studied at the times of Newton by somebody, a colleague, probably Hooke, I don't remember. Anyway, this was a very old, the central case was a very old result, and we extended to all -2. Well, we also have a theory for non-variational Lagrange equations. These are called after Lagrange, not Euler. These are called after Lagrange. And by them, well, I don't even look at the details. We consider hydraulic resistance. And here we prove the contrary. We can give a priori estimates to have explosions in the past. Only if the potential is bounded, if the initial kinetic energy is greater or equal than the sup of the supremum of the potential, then you have explosion in the past, as you have in the scalar case, MQ2 dot. This scalar case, you have an explicit logarithmic solution. You have explosion. Well, you have in any case by our stuff. I go explosion in the past. Well, we also consider dissipative Maxwell block. Well, finally, I'm glad to mention Matthias Comparin, who is a young physicist who is working on our stuff. He already generalized to higher order Lagrangian dynamics, not only second order, but any order, and found also some first results. And he adapted to Euler-Lagrange PDEs, so to the fields. And the paper is going to appear in the reports of mathematical physics soon. Everything I said, and something more, can be seen in this paper, Well, not everything, because there is also that small thing of Poincar's half plane, which is in the monthly. But anyway, this is a survey of many results, which include the dissipative case, which was in a journal of analysis presented by Mowen. And the other one in the Sao Paulo that I told you before, and other results, everything you can find shortly in this paper. I'm glad to be here after a few years. The first time I was in this institute was 1983, November, and I met Sonia and Magnier 1983. It was November 1983, so almost 40 years ago. Glad to be here. Thank you.
So, are there questions, remarks? Eu não estou vendo as perguntas no YouTube, mas, enfim, dessa vez eu não, não consegui me organizar. Acho que podemos... Okay, so if there are no questions or remarks, let's thank the speaker again.